Hello everyone, once again welcome to my YouTube channel Physics with Dr. Sanjay Bhargav. In this video, we are going to study about the fabrication techniques of monolithic microwave integrated circuits. In the fabrication techniques, we'll study epitaxial growth through vapor phase epitaxy, liquid phase epitaxy, molecular beam epitaxy. We are also going to study about the process of diffusion and ion implantation. We'll study metallization by physical vapor deposition, DC sputtering, ion beam deposition. Here we will also study about lithography and the process of etching and photoresist. So here we begin with fabrication techniques for monolithic integrated circuits. Monolithic microwave integrated circuits MMICs can be fabricated by following different techniques like epitaxial growth. Epitaxial growth through the process of liquid phase epitaxy, vapor phase epitaxy and the molecular beam epitaxy. We'll here also study the growth process through diffusion and ion implantation. Then we'll talk about metallization through the process of physical vapor deposition, DC sputtering, ion beam deposition. We'll also study about lithography, etching and photoresist. Now let us begin with the growth of epitaxial layers on substrates. For MMIC, a layer of semiconductor is grown on a single crystal lattice matched substrate, and this process is known as epitaxy technology. The various common processes that we use are the vapor phase epitaxy, liquid phase epitaxy and the molecular beam epitaxy, as already communicated to you. So here the major requirement is we grow semiconductor on single crystal lattice matched substrate. This is the major requirement of epitaxial growth. Let us first pick up liquid phase epitaxy. In this process, when a solution of few percent of arsenic is in molten gallium is cooled down, gallium arsenide crystallizes. The solution can be supercooled to a few degrees below the temperature where liquid and solid are in equilibrium. So in the first step, what we do, we use a solution of few percent of arsenic in molten gallium is cooled down, then crystallization of gallium arsenide takes place. The solution can be supercooled to a few degrees below the temperature where liquid and solid are in equilibrium. When the supercooled solution is brought in contact with a seed crystal, then crystallization starts and continues until the equilibrium temperature is reached. The subsequent crystallization creates an epitaxial layer. So what is the process? The process says when the supercooled solution is brought in contact with a seed crystal, so you require a seed crystal, the process of crystallization starts and continues until the equilibrium temperature is reached. The subsequent crystallization creates an epitaxial layer. This process is slow, no doubt, but is very useful for highly doped samples where layer thickness of greater than 0.2 micrometer are required. So this process is slow but definitely very useful for highly doped samples where the layer thickness is greater than 0.2 micrometer. It is useful where multi-layered structures are required. What is the major drawback of this technique? So in liquid phase epitaxy, it is difficult to control the layer thickness very accurately. So control of the layer thickness is not very precise. The layer could not be made uniform over large wafer area, and interfaces between layers of different composition are not sharp. So another difficulty that is coming up is the layer could not be made uniform. So we do not have uniformity in the layers that have been grown over large wafer area, and interfaces between layers of different composition are not sharp. So with these drawbacks, but is still a helpful one. The second process that we want to know about is the Vapour Phase Epitaxy. So VPE, this is most widely used for growing the layers for microwave devices and MMICs because it provides better surface quality. So this is one of the important property. It provides better surface quality and layer thickness control. The drawbacks of LPE have been overtaken here. So we have better surface quality and layer thickness control is better in LPE, that is the liquid phase epitaxy. In vapor phase epitaxy, the gallium vapors are deposited on the substrate at elevated temperature. So gallium vapors are deposited on the surface at elevated temperatures. Now this figure shows two techniques. One of them a 3-zone furnace and the other is a 2-zone furnace. The 3-zone furnace has 3 zones: the gallium zone, the reaction zone and the deposition zone. While the 2-zone furnace, it has 2 zones, basically the gallium source and the substrate. Let us discuss about how they work upon. A typical 3-zone furnace as shown in the figure A. In the gallium zone, the HCl reacts with the gallium at 75 degrees centigrade and produces gallium chloride GaCl3 gas, which is mixed with AsH3 for doping if needed. In the reaction zone at 850 degrees centigrade, these gases reach the deposition zone where the substrate is put at a lower temperature of about 750 degrees centigrade and hence deposits as an epilayer. A typical 2-zone furnace is also shown in figure B. In the reaction zone, gallium is evaporated at 850 degrees centigrade. The vapor of the gallium reach the deposition zone maintained at a relatively lower temperature, 750 plus minus 20 degrees centigrade. Consequently, the vapors condense as epilayers on the substrate. So, one of the more important methods is the Vapour Phase Epitaxy, and the most sophisticated method is the Molecular Beam Epitaxy. So, the third process through which the MMICs can be grown. The basic structure is shown in the figure. It consists of a stainless steel bell jar system with ions pumped beam in an ultra vacuum of 10 raised to power minus 11 torr. So here in the figure we look here, we have sources present here, we have a substrate on which the deposition takes place. This is the pressure indicator, this is the vacuum pump where a continuous vacuum is maintained to the order of 10 raised to power minus 11 torr. This gives me an inlet of liquid nitrogen for cooling the substrate. Around the substrate, it is cooled by liquid nitrogen. So liquid nitrogen used for cooling the substrate. The elements required to grow layer are evaporated from the so-called effusion furnaces. That is the tubes of an inert material such as tungsten, which are heated to a temperature at which the contents slowly evaporate. The beam of the particles arrive at the substrate and combine there to form desired material. The substrate is heated from 300 degrees centigrade to 700 degrees centigrade to obtain microcrystalline layers. The deposition of about 1 atomic layer per second takes place with well-defined sharp surface. So it is possible to achieve precise control of concentration and doping profile. It can be used in growing multi-layer structures. So we obtain a precise control on concentration and doping profile. It is used in growing multi-layer structures. By molecular beam epitaxy, it provides good material quality, extremely sharp interface. So these are the high order utilities: good material quality, extremely sharp interface, and high degree of uniformity. One of the best methods to grow epitaxial layers is molecular beam epitaxy. Then we have the second part, deposition through diffusion and ion implantation. Diffusion and ion implantation are used to introduce controlled amount of dopants in the semiconductors. Diffusion of impurities is carried out under controlled atmospheric conditions at elevated temperatures around 800 to 1250 degrees centigrades. The temperature is precisely controlled to plus minus 0.5 degrees centigrade. It is very necessary to control the temperature time to obtain a predictable junction depth in a doped semiconductor. The impurity vapors diffuse into the substrate vapor and desired doping is achieved. Another technique is the ion implantation technique, whose figure is just shown here. So we have an ion source, we have a vacuum jacket, we have a substrate here. This is the target. The ions bombard on the target and the vapor is produced, which is then deposited on the substrate. Ion implantation is another technique used in process of doping. It is better technique because it allows precise control of doping plus minus 1% with multi-layer in-depth doping. In this technique, a beam of ions is accelerated to higher energies around 100 kilo electron volt. The ions to be doped at a particular layer are magnetically separated and finally directed to the substrate. Since the de Broglie wavelength of the ions is comparable to the lattice distance, ions get implanted. In the process, the crystal lattice is severely damaged by the highly energetic ions. Then the subsequent annealing of the vapor at a temperature around 900 degrees centigrade repairs such damages. The schematic diagram was shown on the earlier page. Now let us come to another process of metallization. I do hope that the videos are useful for you. In case the videos are useful and you are understanding physics out of it, you are requested to subscribe and like the videos. You can press the bell icon button so that you can receive a notification as and when the video is uploaded. Now come to process of metallization. What is metallization? Metallization is the process of depositing a thick metal film on the substrate, both for circuit elements and the ground plane. The different processes that are used for metallization are physical vapor deposition. In this process, the metal to be deposited is put in a hearth boat placed in a vacuum chamber of the pressure 5 into 10 raised to power minus 7 torr. The hearth is heated either by filament or by induction. So these are the two processes by which we are heating, either by filament or by induction heating, using RF source or by electron beam impact at the center of the hearth. The evaporated metal atom deposit on the substrate, forming a polycrystalline layer on it. So heating could either be done by filament or by induction or by using a RF source or by electron beam impact. So these are the different ways by which you can produce heat. Another method that we talk about is DC sputtering. In this process, a high voltage DC is applied between the crucible containing the metal and the substrate anode. In this figure, we have an RF source, we have a high voltage DC source. Through this inlet, the gases, that is the inert gas, is made to move in of the chamber. This represents the duct for the vacuum pump. This is the target metal to be deposited in heated earth. This represents the earth, this is the target material, and these are the wafers on which these evaporated part would be deposited. Vacuum of the order of 10 raised to power minus 3 torr is maintained in the vacuum chamber in which the metal and substrate are placed. A slight trace of argon gas is introduced in the chamber. Under low pressure and high applied voltage, a glow discharge of argon gas is formed. The argon ions so generated are accelerated towards the cathode. The impact of argon ion on metal dislodges the metal atoms via momentum transfer. These metal atoms fly through the thin gas atmosphere and subsequently attach to the oppositely charged substrate located just in front of it. So, this method is also useful in deposition. Then for metallization, the other process or the third process is the ion beam deposition, which we have already studied in the form of ion implantation earlier. Now we come to the process of lithography. In this process, a photosensitive layer is coated on the semiconductor surface and other proper preparation, and after proper preparation, this organic lacquer layer is exposed to some appropriate radiation, either UV, deep UV, electron beam, ion beam, laser and X-rays through right kind of mask which produces positive or negative image of the pattern on the mask. Lithography is the process of transferring patterns of geometric shapes on the mask to a thin layer of radiation sensitive material, which is known as resist, for covering the surface of a semiconductor wafer. The resist patterns defined by lithographic process are not permanent elements of final device by only replicas of the circuit features. There are 4 types of lithography technology: electron beam lithography, optical lithography, ion beam lithography and X-ray lithography. In the last, we discussed about the processes of etching and photoresist. In the process of making MICs, a selective removal of SiO2 is required in order to form openings through which impurities can be diffused. The typical diagram for photo etching process are shown here. So this represents the substrate, that is the silicon chip. We have a black layer of photoresist and a masking layer. On this we can send ultraviolet radiation. This is the process of masking and exposure to the ultraviolet radiation. Then we have this as the layer of SiO2, this as the layer of photoresist, polymerized photoresist. This is substrate. During the photolithographic process, the substrate is coated with a uniform film of Kodak photoresist KPR, which is a photosensitive emulsion. A mask for the desired opening is placed over the photoresist and ultraviolet light exposes the photoresist through the mask as shown in the figure A. A polymerized photoresist is developed and unpolymerized portion are dissolved using trichloroethylene after the mask is removed as shown in the figure B. The SiO2, which is not covered by the photoresist, can be removed by hydrofluoric acid. The process usually involves printing and silk screening of silver or gold through a metal mask in a glass fret, which is applied on the ceramic and fired at 850 degrees centigrade. After firing, the initial layer may be covered with gold. Now let us pick up a fabrication example. The fabrication processes include the following. First part, deposition. An oxide layer is deposited on the semiconductor material and then a photoresist layer is deposited to cover the oxide on the top of the semiconductor chip. So first part is deposition. So In this figure also, the first part is deposition. Second part is masking. Let us talk about it. Ultraviolet light is used to shine through a precision photographic mask to the photoresist. Then the third part is the chemical etching. Chemical etching with hydrofluoric acid is used to remove the selected oxide region. And the fourth part is etching. The photoresist is finally dissolved with an organic solvent in the oxide, leaving the desired opening. That is how we fabricate MMICs. I hope this video makes you clear about the various fabrication techniques related to microwave monolithic integrated circuits. If you like the video, you understand my physics, then you are all requested once again to subscribe the channel, like the videos, press the bell icon button so that you can receive the information or notification about the future uploaded videos. Thank you very much.